I'd like to welcome you to this lesson. In this lesson, we're going to provide an introduction to processor scheduling and how it affects our various system components and to integration of it within the previous concepts that we have discussed. And so some general topics that we will be discussing over the next couple of lessons include process as an abstraction, and in this we'll be discussing what exactly constitutes a process when it is executing on a system. We'll discuss the idea of a scheduler, what a scheduler does, and how it operates. We'll be sure to differentiate between a process, a job, and a thread, and a task, specifically gaining a detailed understanding of how they are different from one another. We'll provide an overview and insight into the states of processes. We will introduce a process control block and how it is utilized by schedulers. We'll discuss the types of schedulers that are available, and we will understand various metrics that can be utilized to analyze the performance. We will also discuss appropriate scheduling algorithms that can be utilized. And we will also provide for a high-level evaluation of the various schedulers. And so before we dive into scheduling, let's first take a second to think, what exactly is an operating system? And you want to consider that an operating system layers a partial abstraction on the instruction set architecture. And so it's commonly referred to as OSML, which is a operating system machine level, and that was first denoted by Tannenbaum. But what are the specific abstractions that are provided by an operating system? At a high level, an operating system allows for multiple processes to occur and execute. And this is behind the idea of having one physical processor that can run multiple programs at the same time. An operating system is also responsible for providing appropriate memory permissions that enable other processes in the OS to be protected. A chief responsibility of an operating system is also to provide appropriate access to shared devices such as I/O devices, networks, and file systems that need to be utilized by the system. Operating systems also provide for appropriate resource sharing. This occurs by sharing, allowing for various system components such as processors, memory, I/O, networks, and etc. to be shared. In addition, there are additional components and instructions that can be implemented through traps. These include read, write, exit, and other types of permissions that can be changed. And so although we'll be focusing on the operating system, it's important to keep in mind that the ISA is still an important part. The OS doesn't completely obscure or hide the abstraction. And when we talk about the levels of abstraction, we've talked about the application and how it's expressed at a high level. We've talked about system software at a high level, but now we'll go into detail on how the compiler and operating system interact with one another. We've talked specifically about the computer architecture components with regards to the instruction set architecture, as well as data path and control mechanisms that relate to machine organization. And so now we'll be able to take a look in more detail with regards to system software and how it interacts with the ISA. Specifically, we want to be able to provide an understanding of how the compiler and the operating system have to work together. And so let's first consider how is a program represented in memory. And with this regards, we want to keep in mind that a program has a purpose and that it needs to utilize appropriate resources in order to execute the user's commands. And so this relies on a number of different resource requirements that need to be utilized by the program. And so let's consider the type of resources that are needed. We need to take into consideration that when we put a program in memory, that there are going to be various components that are utilized by the system and the operating system. So if we were to consider something like a C program, then we need to have a good understanding of how the processes will execute going down from the top. And this is accomplished by utilizing the operating system, and to a degree machine code can be used that's generated by the compiler to allocate appropriate resources for the sharing of appropriate data. And so what are some things that we need to keep in mind when it comes to creating a program, or how exactly is a program created? Well, first, we know that we have a problem specification that's given. And as a human, we can interpret that problem specification that allows for us to develop an appropriate algorithm. Once we have the algorithm developer, we'll use our appropriate tools, such as an IDE or an editor, to create the appropriate code for that program. Once we've created the code, we've codified our solution into a appropriate program, and C will need to make use of an appropriate compiler. We utilize the compiler to compile the C code to produce a binary representation of the program that can be utilized. So once we have the binary representation, we're going to have it be utilized by a linker in order to provide for an appropriate executable that can be utilized. And the linker is going to need to not only make use of the compiled binary code, but any appropriate additional libraries that may be needed by the program for execution. Once the program is translated into an appropriate executable binary, it can then be utilized and represented in memory. And so we can have different representations for our program, but the loader is what is going to be utilized to load it into memory. And so when we talk about memory footprint, then it's important to keep in mind that we've kind of reached the end of the program creation process, and that the program is now readily available in memory. And so what exactly does this mean, and how is a program represented in memory. Well, in order to discuss that, let's first pay attention to what are some of the differences between a process and a program. And so when we think about a process, it's important to understand that a process is simply a program in execution. And so, and it's important to keep this in mind because a process is going to represent the entire state of a program in execution. And that state means that the current register utilization, its current location in memory, the current status of the program counter, and what is available on the stack. So once a program starts executing, we have the contents of memory that are going to be occupied by the program. And as the execution of the program changes, its state is going to change. And this might allow for the different processes to register as well. And so thus far, when we've been working, we've been talking about computers that are executing a single process with the LC 2200 ISA. But we know that this isn't a realistic way that computers and programs operate. And previously, we got our first clue to this when we discuss interrupts and how they operate. And so essentially what you want to remember and keep in mind is that a process is a program and it is going to represent the entire state of the program during execution. And it's important to differentiate that a process is going to change as the program execution changes and evolves. And so let's have a little quiz. Um, a process differs from a program in that A, there is no difference. B, process is a machine language representation of a program. C, a process is a program in execution. D, a process is a program that executes correctly. E, a process is a special kind of program that is part of the operating system. Or F, no clue. Well, we just gave a high-level overview of what exactly a process is. And the main thing that you want to be sure to keep in mind is that a process is going to be representative of a program in execution. And so the correct answer here is going to be C. So now we will discuss some additional concepts related to multitasking. And with multitasking, we're going to get into more detailed discussions and different algorithms that can be used. But first, let's consider that what do we mean by when we say multitasking? And what we mean is multitasking is a way of running multiple processes. And so this means that uh, our system is able to make use of various resources at the same time to do different tasks. And so let's consider multitasking in the context of our day-to-day life. There are different things that we have to do on a daily basis. And, just for example, we have to do various tasks like laundry, we have to prepare food, call your loved ones, um, prepare for tests. There are many other things that we have to do, and we have to multitask and allocate resources appropriately as needed. That provides us with a good way to contextualize what we mean by multitasking. And so, exactly what is the best way to timeshare the resources that you have available? And so, in this regard, let's consider what it means to multitask in a computer world. And so, there are various tasks that we're able to do on our systems. And systems can be computers, it can be your tablet, it can be your phone or mobile device. And these different tasks or include, use sending emails, browsing websites, recreational activities, playing games, Facebook or Snapchat or Instagram. And these resources need to utilize the CPU in order to execute. And so, how do we timeshare a processor? There are different things that you have to consider in order to accomplish this. And so, you know, if we want to think about each of these different tasks, we can organize them as different programs. And so we can say program one to program N. Now, how are these various programs going to run on our system? Well, in order to do this, we have to make use of what is called a scheduler. And so a scheduler allows various sets of processes to make use of a processor and additional properties in our system. And so we have to consider the system and different properties that are needed in order for our various tasks to execute. And so this can depend on what resources are available. And resources um, can be based off of specific requirements, memory requirements of the program that are needed, um, time considerations, um, and, and also what system components are available. And these would be representative of not only intrinsic properties of the system, but extrinsic properties also that, that are based off of the task. And so this provides for a mechanism for a scheduler to analyze the program, the system, and properties that are needed for each task to execute. And in many cases, what we have to consider is what is required in order for that task to execute. Okay, so now we have another question. A scheduler is what? A is a part of the operating system that makes decisions to allocate the processor resource to processes. B is a piece of hardware. C is an instruction in the ISA of the processor. D, a scheduler tells me when to call mom. And so one thing that you want to keep in mind is that a scheduler is part of the operating system that can be utilized to make decisions to allocate the processor resource to processes. And so you've also probably heard the term threads, and threads can be utilized in order to allow for multiple uh, processes to execute. And so this is, we'll get into this in more detail, but this basically allows for various programs to share different resources on a processor and on the system. And various chips can have different configurations for the way that they have threads enabled. So you can have you can have a chip that can have multiple cores, and each core can have multiple threads. So different processes are able to execute in that manner. And so let's kind of break down the terminology in this regard. We want to consider a job is going to represent a unit of scheduling. And within the work that we're doing in this chapter, it's going to be synonymous with the process. And so then we have a process. A process is simply a program and execution and a unit of scheduling. And this is going to be synonymous with the job. Then we have thread. Thread is going to represent a unit of scheduling and or execution. And a thread is contained within a process. And so we also have a task, and you want to keep in mind a task is a unit of work or a unit of scheduling. Threads and tasks are not necessarily going to be utilized in this chapter, but they should be terms that you have heard explicitly in use in your daily life or working with computers. So what exactly do we mean by a scheduler? And so you want to keep in mind that a processor is likely going to have a specific set of tasks. And so a scheduler can be utilized to understand the environment that the processor and system components are operating in. And so this would allow for uh, scheduling to determine the appropriate mechanism in which a specific task can be executed on a processor and in memory. And so there are different types of scheduling algorithms that are available. And so an overview of them, we can have a long-term scheduler, which is mainly focused on batch-oriented processes. And so in this way, a long-term scheduler provides for the ability to control various jobs in memory, and this allows for appropriate resources to be balanced. You'll have also an appropriate a medium-term scheduler. And most medium-term schedulers are most operating systems have medium-term schedulers, and these are used in order to help provide for a mixture of appropriate processes in memory, and it can help to avoid thrashing or any type of overutilization of resources. We'll have also short-term schedulers as well, and that will be the primary focus of what we're going to be working with for the next couple of lessons. And they're contained in every modern operating system, and they're used to schedule the memory resident processes on the CPU that need to be used. And so other components include dispatcher, and the dispatcher is used in order to populate the CPU registers with the current state of the process that needs to execute by the short-term scheduler. We also have loaders that are um, used to load programs from disk and into memory as well. And so this is just an overview of those various components and the terminology associated with them. And so another question, in most modern day operating systems, we want to consider that there is exactly one program in residence in memory at any point in time. There are multiple programs in residence in memory at any point in time. There is exactly one program, but multiple processes in residence in memory at any point in time. Or does your head hurt? And so you want to consider what is the structure of operating systems. And in this case, the correct answer is going to be B. There are multiple programs in residence in memory at any point in time. And so another question, in the execution of a program, there A is exactly one active entity called a process. B could be multiple active entities called threads. C are two active entities, one a thread and the other a process. And so with this in mind, we want to consider that there could be multiple active entities, and they would be called threads. And so we want to consider, we've introduced the idea of processes, tasks, and threads and jobs. So what exactly occurs when a process, or what does a process do when it is executing on our system? And a pretty straightforward example that might be a little outdated is reading music from from a CD. Uh, well, now it's all done from MP3s or streamed, but essentially what happened is you initiate reading the music track from the CD. That results in a CPU burst. We read a music track from the actual CD. That results in an IO burst. And then we need to process and render the track to speaker and also initiate reading the next track from the CD. And that's going to result in another CPU burst. And then we need to render music to speaker and continue to read and process the music from the CD. And that'll be another IO burst. And so we want to continue the types of bursts that are taken into account. And when we say a burst, what we're doing is denoting the amount of time a process would run without making, for a CPU, without making an IO call. And then we'll basically denote that a CPU burst of a process is the time interval of continuous activity on the CPU by that process before it makes an IO call. And so one way to think about is a CPU burst would be the amount of time that you would do um, something like continuously studying before you take a break, or doing an activity like exercising before you stop to get a drink of water. That is going to be representative of a CPU burst. And you also want to keep in mind appropriate CPU to IO ratios and their utilization. And so you want to keep in mind that the memory footprint of a user program is going to be representative of the program global data. And we'll also be making use of the OS for IVT as well as for IO as well. And so what are some considerations that we make when we talk about a process state? We want to keep in mind specific properties that relate to the way a scheduler is utilized. And we want to have a good understanding of how a process receives priority and what is going to be the expected time that the program will execute and how long the program is needed. So this also requires us to keep track of other components, what registers are needed, what is the status of the program counter, and what is the status of the stack pointer. And so overall, it's just what is the state of the process being executed. And in this case, it is P2 that is being executed from memory. So essentially, this means that we need a appropriate mechanism or structure that we can utilize in order to represent a process's state. So what we would come up with is what we call a structure that is going to be called a process control block. And so what exactly is a process control block? It's a way for us to account for the current state of a program. And so in this case, we want to make sure that we're able to capture the intrinsic and extrinsic properties of a process so that the scheduler can make appropriate decisions with regards to the priority of that process, when it should execute in our in the program, um, and also the overall expected execution time. And so we have appropriate mechanisms that can be put in place that can account for each of these components to represent the state of the process. And that is what is used in order to schedule the process for execution on the on the processor. Okay, and so another question is, one of these is not part of the process control block. And so A, is it going to be general purpose registers that are visible to the instruction set? B, program counter and the register that represents the stack? C, the layout of the program in memory? D, internal registers in the data path of the processor? Or E, priority information? And so which one of these is not part of the process control block? And in this case, the answer is D. We don't need internal registers in the data path of the processor. We'll need all other components. We need to know what registers are being used via the register file. We need the status of the PC and the stack pointer. We'll need an understanding of where the process is in memory, and we will need appropriate information for establishing priority. And so we'll also need to include appropriate mechanisms that are used to represent the volatile state of the process. And then this is the address of the program counter, as well as appropriate registers that are being utilized. And so we want to consider that we will need an appropriate mechanism in order to represent uh, represent the state or the execution of the process control block. And this is what is going to be utilized by the scheduler to pick the process that will execute. And this is going to be done so that we can analyze what available system resources are available for the CPU to use. And it's going to what's guide the priority of the process that gets executed. So in order to do this, we make use of two linked lists. And one linked list is going to be representative of all the processes that are actually ready to execute on the processor. And appropriately, we're going to call that the ready queue. Um, and basically, when we say that they're ready, that means that they're not waiting on any resources. They're not waiting on additional memory to be made available. They are, given the current state of the system, they are ready to execute. And so as soon as the CPU has time, then they can be executed. And so the scheduler is basically going to choose the winner based on the expected time of the task to execute. And that is what's going to be put at the head of the list. And so the appropriate steps in scheduling vary. You want to be able to divide appropriate processes into either non-preemptive or preemptive scheduling task. And so preemptive means that they need external interrupts, and non-preemptive mean that they are representative of either system calls, IO requests, or process exits. And so you could think about it is that with a non-preemptive scheduler, you're going to have a process. It's going to execute um, completely until it's done, or it's going to be forced to. It's going to force to give up the processor to a task to the non-preemptive task, the system call. If a task is taken away from a processor and given to another process, then it's considered a preemptive scheduled task. And so next you need to save the state of the current processor, and that means that we need to dump the state into the process control block of the that's currently executing. And so this allows for appropriate information to be obtained. Then we'll need to select a new process to run. And so this is this with the short-term scheduling algorithm, we select a PC process control block that is going to be dispatched. And when we say dispatched, what we mean is that we're going to need to load the state of the selected PCB into the processor registers for execution. And so when we consider this entire process, from grabbing the attention of the processor to saving the state of the current process, selecting a new process to run, and then the dispatch of the process, we call these entire steps a context switch. Okay, and so some things that we want to keep in mind, we have some terminology that we discuss related to CPU bursts. This is going to be representative of a continuous CPU activity by a process before requiring an I/O operation. We have I/O bursts, and that's going to be the activity initiated by the CPU on an I/O device. We have defined or process control block, and a process control block that is going to hold the state of a process. We have our ready queue, and it's a queue of the PCBs that are going to represent the set of memory resident processes that are ready to run on the CPU. We have our IO queue, and that's going to be a queue of PCBs to represent the set of memory resident processes that are waiting for IO operation either to be initiated or completed. And then we have our appropriate non-preemptive and preemptive algorithms that are used to allow, non-preemptive is used to allow currently scheduled process on the CPU to relinquish their processor, and preemptive is used to forcibly take processors away from a currently scheduled process because of a external event. And then we've also discussed thrashing, which involves dynamic memory usage of the process. And so in our next discussion, in our next lesson, we will discuss appropriate considerations that can be made in regards to appropriate metrics that we can utilize